Out there in the frozen darkness beyond Neptune, drifting silently through the Kuiper Belt, lies a world so strange it defies explanation. Orcus, a name borrowed from the Roman god of the underworld, lives up to its ominous title. This dwarf planet, discovered in 2004, isn't just another icy rock at the edge of our solar system. It's a place of bizarre contradictions, a celestial puzzle that has left astronomers scratching their heads for nearly 2 decades. Picture this, an object roughly the size of Pluto with its own moon, yet so mysteriously reflective it gleams like a cosmic mirror in the void. But that's just the beginning. Orcus hides secrets that challenge everything we think we know about the outer solar system, secrets we're only starting to unravel. What makes Orcus so captivating isn't just its distance or its icy surface, it's the sheer number of unanswered questions surrounding it. Why does its orbit mirror Pluto's almost perfectly, as if locked in some celestial dance? How does a world so far from the sun manage to maintain such startling brightness? And perhaps most haunting of all, what unseen forces could be at work in its dark, uncharted expanse? Some theories suggest hidden oceans beneath its frozen crust. Others whisper of ancient collisions that reshaped its fate. But one thing's certain, Orcus isn't playing by the rules. Every observation deepens the mystery, leaving scientists torn between excitement and frustration as they piece together clues from across the cosmos. Today, we're setting off on a journey to explore the 25 greatest enigmas of this distant world. From its peculiar orbital resonance to the haunting whispers of unknown materials on its surface, each mystery pulls us deeper into the unknown. We'll dive into the latest research, confront baffling anomalies, and even question whether Orcus could rewrite our understanding of the Kuiper Belt itself. This isn't just a tour of scientific facts, it's an expedition into one of space's most bewildering frontiers. So buckle up. By the time we're done, you'll see the solar system's outer reaches in a whole new light. And who knows, you might just find yourself staring at the night sky, wondering what other secrets Orcus and the universe are still hiding. One of the most striking mysteries of Orcus isn't just its brightness, it's that eerie red spot staining its otherwise pale surface. Like a cosmic bloodstain against the ice, this strange feature stands out in telescope observations, a puzzle wrapped in frozen darkness. Scientists first noticed it in data from the Hubble Space Telescope and later infrared surveys, revealing a concentrated patch of reddish material unlike anything else in the region. The leading theory, tholins, complex organic molecules created when methane and nitrogen are zapped by solar radiation over millions of years. We've seen these bizarre compounds tint other Kuiper Belt objects like Pluto's famous heart-shaped region. But here's the catch, Orcus shouldn't have enough atmospheric residue for tholins to form so prominently. It's too small, too cold, too isolated. Yet that red spot persists, almost mocking our expectations. Then there's the cryovolcanism angle. Imagine ice volcanoes spewing slushy mixtures of water, ammonia, and other volatiles onto the surface. As these materials freeze and react with cosmic rays, they could create reddish deposits. Europa and Enceladus have shown us how active icy worlds can be, but Orcus, it's supposed to be geologically dead. If cryovolcanoes are at work here, it would mean internal heat sources we can't yet explain, possibly from radioactive decay or ancient tidal forces locking energy beneath the crust. Some researchers even speculate that a massive impact long ago could have churned up buried organics, splattering them across the landscape like paint. What makes this spot so unsettling is how it defies every model. It doesn't match the distribution patterns of tholins seen elsewhere. It's too localized, too vivid. New Horizons' flyby of Pluto gave us a blueprint for how these processes should work, yet Orcus plays by different rules. Every time we point a telescope at it, the data raises more questions. Could there be exotic chemistry at play, something we've never encountered before? Or is this the scar of some cataclysmic event lost to time? One thing's certain, that crimson smudge is a silent challenge, daring us to rethink what's possible in the outer solar system. If there's one thing that makes Orcus stand out even among the weirdest objects in the Kuiper Belt, it's the way it moves. This dwarf planet doesn't just orbit the Sun. It performs an intricate gravitational ballet, locked in what's known as a 2-to-3 resonance with Neptune. For every 2 trips Neptune makes around the Sun, Orcus completes 3, tracing a path that mirrors Pluto's orbit with uncanny precision. But here's the twist. While Pluto's relationship with Neptune is well documented, Orcus shouldn't be stable enough to maintain this dance. The math says it ought to have been flung into chaos long ago, yet it persists, defying the odds with every silent revolution. This orbital mystery isn't just a cosmic coincidence, it's a window into the solar system's violent past. The leading theory suggests that, like Pluto, Orcus was nudged into this resonant orbit by Neptune's gravitational pull during the giant planet's migration billions of years ago. But the devil's in the details. Pluto's resonance is reinforced by its sheer size and momentum, acting like a gravitational anchor. Orcus, on the other hand, is smaller, lighter, and far more vulnerable to disruptions. So why hasn't it strayed? Some scientists speculate that an ancient collision might have altered its trajectory, locking it into this perfect rhythm. Others propose hidden forces, perhaps the collective tug of other Kuiper Belt objects, or even the faint influence of the hypothetical planet 9 helping it stay in sync. What's even stranger is how Orcus's orbit avoids Neptune's direct influence. Unlike Pluto, which occasionally dips closer to Neptune than any other planet, Orcus keeps a cautious distance, its path tilted at an angle that prevents close encounters. This orbital inclination is yet another puzzle. Did it form this way, or was it engineered by unseen perturbations over eons? The answer could rewrite our understanding of how small bodies survive in the outer solar system. Then there's the question of longevity. Resonances like this are fragile. Over time, gravitational nudges from other planets should destabilize them. Yet Orcus has clung to its rhythm for billions of years, outlasting countless other objects that succumb to chaos. Is it sheer luck, or is there some unseen mechanism at work? Recent simulations suggest that Orcus might occupy a sweet spot, in the resonance, a narrow zone where Neptune's tugs cancel out over time, creating a pocket of stability. If true, it would mean the Kuiper Belt is far more finely tuned than we ever imagined. The implications are staggering. If Orcus's orbit holds secrets about Neptune's early migration, it could help us piece together the solar system's turbulent adolescence. And if hidden forces are at play, we might be on the verge of uncovering new physics governing the outer darkness. One thing's clear, Orcus isn't just following the rules, it's revealing how little we truly understand them. Every loop around the Sun is a silent challenge, daring us to decode the cosmos's hidden rhythms. Just when we thought Orcus couldn't get any stranger, astronomers stumbled upon a rumor in the data, a ghostly whisper of a second moon. Meet Vanth, the disputed companion that might, or might not, be orbiting this enigmatic dwarf planet. The story begins with Hubble's keen eye. In 2008, while studying Orcus and its confirmed moon Vanth, researchers noticed an extra speck of light lingering at the edge of their frames. Too faint to be a star, too close to be a coincidence, this blip seemed to trace Orcus's path. The name Vanth was tentatively assigned, sparking a debate that's divided scientists ever since. Supporters of the Vanth hypothesis point to Hubble's track record. This telescope has spotted moons around other distant worlds, like Pluto's tiny satellites Nix and Hydra. The data showed Vanth at a consistent distance from Orcus in multiple observations, suggesting it wasn't just cosmic noise. Even more intriguing, its orbit appeared wildly tilted. Unlike Vanth's near-perfect circle, Van's path would be erratic, looping around Orcus at a steep angle. If real, this could mean Van was a captured object, a wanderer snagged by Orcus's gravity in the early solar system. But skeptics aren't convinced. They argue the signal is too weak, buried in Hubble's instrumental noise. When other telescopes tried to confirm Van's existence, they came up empty. The Keck Observatory in Hawaii, equipped with cutting-edge adaptive optics, saw nothing but empty space where Van should have been. Critics suggest the original detection might have been a glitch, a cosmic ray hitting Hubble's sensor, or a flaw in image processing. Even the tilt of Van's supposed orbit raises eyebrows. Moons with such extreme inclinations are rare, especially around small bodies like Orcus. Without more evidence, Van risks becoming another footnote in astronomy's graveyard of unconfirmed discoveries. Yet the mystery lingers. If Van is real, it could rewrite how we understand moon formation in the Kuiper Belt. Most binary systems out there, like Pluto and Charon, are thought to be born from giant impacts. But a second moon, that would imply Orcus had a far more chaotic past, possibly surviving multiple collisions or gravitational encounters. Some theorists even propose Van could be a fragment of a larger moon shattered by an ancient crash, a survivor of orbital warfare we can barely imagine. For now, Van remains in limbo, a celestial maybe. Future telescopes like NASA's upcoming Nancy Grace Roman Space Telescope might settle the debate once and for all. Until then, this phantom moon serves as a reminder. Even in an age of advanced astronomy, the outer solar system still keeps secrets. Whether it's noise or reality, Van embodies the tantalizing uncertainty that makes Orcus so endlessly fascinating. While Orcus gleams like a frozen mirror in the void, its moon Vanth tells a different story, one written in shadows. This enigmatic companion isn't just darker than its parent world. It's coated in something far more primitive, a layer of carbon-rich material that hints at a violent past. Picture charcoal smeared across an icy canvas, absorbing sunlight instead of reflecting it. Spectroscopic studies reveal Vanth's surface is packed with complex hydrocarbons, a stark contrast to Orcus's bright mix of water, ice, and ammonia. How could two objects locked in the same orbit be so fundamentally different? The leading theory suggests Vanth wasn't born alongside Orcus at all. It might be a captured relic from the Kuiper Belt's darkest corners. Objects like Makemake and Haumea show similar brightness to Orcus, but Vanth's composition aligns more closely with the so-called ultra-red trans-Neptunian objects, which are thought to be coated in ancient organic gunk. If true, Vanth could be a time capsule from the solar system's infancy, a wanderer snagged by Orcus's gravity billions of years ago. Supporting this idea is Vanth's unusually large size for a moon of its parent body, almost one-third the diameter of Orcus itself. Most captured moons are tiny, like Mars's irregularly shaped Deimos and Phobos. Vanth's bulk suggests a dramatic encounter, possibly a slow-motion collision or a gravitational tug-of-war that left it stranded in orbit. But there's another, darker possibility. Vanth's carbon coating might be the debris of an ancient cataclysm, a collision so violent it shattered a precursor moon, leaving behind a corpse stained with its own remains. When comets or carbon-rich asteroids collide, they can scatter dark material across surfaces like cosmic soot. We've seen this on Saturn's moon Iapetus, where one hemisphere is stained pitch black by dust from smaller satellites. If something similar happened to Vanth, it would explain both its odd composition and its unusually tight orbit. Some models even suggest Vanth could be the remnant core of a larger body, its icy mantle blasted away by the impact, leaving behind a dark, carbon-heavy skeleton. Then there's the radiation angle. Over billions of years, cosmic rays bombarding Vanth's surface could have transformed simple ices into complex hydrocarbons, a process we've observed on other Kuiper Belt objects. But here's the catch: Orcus, exposed to the same radiation, remains bright. Why would Vanth darken so dramatically? The answer might lie in its rotation. Vanth is tidally locked, always showing the same face to Orcus, meaning one hemisphere bakes in sunlight while the other freezes in eternal shadow. This uneven heating could drive chemical reactions on its sunlit side, cooking its surface into a carbon-rich crust while Orcus, spinning more rapidly, stays pristine. Perhaps the most haunting clue comes from Vanth's spectrum, which shows hints of methanol and cyanide compounds molecules often found in the darkest regions of interstellar space. If these substances are native to Vanth, it could mean this moon formed in a colder, more distant part of the solar system before migrating inward. Or maybe they're the byproducts of eons of radiation, a slow transformation no telescope can yet fully decode. What's clear is that Vanth and Orcus are cosmic opposites, a study in contrasts that defies simple explanation. Whether it's a captured wanderer, a collision survivor, or a radiation-altered relic, Vanth's darkness forces us to confront how little we understand about the chemistry of the outer solar system. Every observation deepens the puzzle, reminding us that even in the frozen dark, the universe keeps its most stubborn secrets close. Orcus didn't just earn its nickname as the Anti-Pluto by chance. This dwarf planet is a cosmic mirror image, reflecting Pluto's most defining traits while flipping them on their head. At first glance, their orbits are nearly identical twins. Both dance in that same 2 to 3 resonance with Neptune, tracing elongated paths that swing them from the inner edge of the Kuiper Belt out into the frozen depths beyond. They're celestial siblings in motion, but here's where the duality begins. While Pluto basks in reddish hues and a heart-shaped plain of nitrogen ice, Orcus stares back with a face like polished bone, its surface gleaming with almost unnatural brightness. Scientists call this the Pluto-Orcus dichotomy, a study in contrasts that goes far deeper than appearance. Pluto's terrain is dynamic, sculpted by glaciers and shifting atmospheres, while Orcus lies eerily still, its icy crust showing few signs of geologic activity. Where Pluto's heart, Tombaugh Regio, oozes with soft nitrogen ice that slowly convects like a lava lamp, Orcus's brightest regions are rigid, dominated by water ice laced with ammonia, a compound rarely seen in such abundance. This isn't just a difference in color or texture, it's a fundamental divergence in chemistry and history. The nickname Anti-Pluto sparks fierce debate, though. Some astronomers argue it oversimplifies the relationship. Yes, their orbits are cosmic doppelgangers, but the label implies opposition where there might just be variation. After all, both worlds share a Kuiper Belt heritage, both have moons, and both defy expectations. Critics of the nickname point out that Orcus isn't Pluto's opposite so much as its alternate universe counterpart, a version of Pluto that took a different evolutionary path. Perhaps it formed in a slightly colder part of the primordial disk, preserving more ammonia. Or maybe a colossal impact stripped away volatile compounds, leaving behind a brighter, icier skeleton. Then there's the albedo enigma. Orcus reflects nearly twice as much sunlight as Pluto, a discrepancy that baffles researchers. Fresh ice exposed by impacts could explain some of it, but not all. Recent studies suggest Orcus might be actively replenishing its surface, with subsurface volatiles bubbling up through cracks or cryovolcanic vents, except no such features have been detected. If true, it would mean Orcus hides geologic secrets even Pluto doesn't possess. The debate over the Anti-Pluto label isn't just semantics, it's a battle over how we classify the outer solar system's weirdos. Call Orcus Pluto's opposite, and you risk ignoring the nuances that make both worlds fascinating. But embrace the nickname, and you highlight a cosmic irony: two neighbors, born from the same chaos, now embodying opposite extremes. Whether you see them as rivals or reflections, one thing's clear: the Kuiper Belt is far stranger and far more diverse than we ever imagined. Among Orcus's many mysteries, few are as visually striking as those anomalous bright patches, glaring spots of light that stand out like beacons against the dwarf planet's already reflective surface. Telescope observations have captured these brilliant regions, some as small as a few kilometers across, scattered unpredictably across the terrain. Unlike the reddish stain we discussed earlier, these patches shimmer with an almost metallic sheen, reflecting sunlight with an intensity that suggests something far purer than ordinary ice. The leading suspect, fresh deposits of water ice, possibly laced with ammonia or methane hydrate, exposed by recent geologic activity or impacts. But here's the puzzle. In the frigid depths of the Kuiper Belt, where temperatures hover near absolute zero, ice shouldn't stay this pristine for long. Cosmic radiation and micrometeorite bombardment should darken these areas within millennia, yet there they gleam, untouched by time. One compelling theory points to cryovolcanism. Imagine fissures cracking open in Orcus's frozen crust, spewing supercooled slush onto the surface. As this mixture of water, ammonia, and other volatiles freezes, it could create bright, smooth plains reminiscent of Europa's icy shell. The presence of ammonia is particularly intriguing. It acts as antifreeze, lowering the melting point of water and allowing sluggish geologic activity even in this deep freeze. But there's a catch. No spacecraft has ever gotten close enough to spot volcanic vents or flow features. All we have are those tantalizing patches of light, their origins inferred from spectral data that hints at crystalline ice, a form usually disrupted by radiation unless recently exposed. Then there's the impact hypothesis. A collision with another Kuiper Belt object could have blasted away Orcus's darker surface layers, revealing untouched ice beneath. We've seen this phenomenon on Saturn's moon Enceladus, where fresh ice from its south polar geysers outshines the rest of the surface. But Orcus's bright patches don't follow the expected patterns. They're not concentrated in craters or ejecta blankets. Instead, they appear in seemingly random clusters, some perched on ridges or slopes where impacts are statistically unlikely. Even stranger, their distribution doesn't match the usual fallout from meteorite strikes. If impacts are the culprit, why don't these bright zones align with any obvious trauma to the landscape? The seasonal argument adds another layer of intrigue. Pluto's surface shifts over its 248-year orbit, with nitrogen snows frosting its poles in winter and sublimating in summer. Could Orcus experience similar cycles? The math says maybe, though its seasons would be far more subtle due to its lack of a substantial atmosphere. Trace gases might still migrate across its surface, freezing onto colder regions and brightening them temporarily. Yet spectra of these patches show no signs of nitrogen or carbon monoxide, the usual seasonal players. Instead, they scream pure water ice, a composition too stubborn to fit neatly into the seasonal model. Perhaps the most radical idea is that these patches are windows into a hidden ocean. Europa and Enceladus taught us that liquid water can lurk beneath icy shells, occasionally erupting to refresh the surface. If Orcus harbors even a sliver of subsurface warmth, perhaps from radioactive decay or tidal heating, it could explain these rejuvenated zones. But without the tidal forces of a giant planet nearby, how could Orcus generate enough energy to keep water liquid? Some researchers speculate that ammonia or salts dissolved in the water might lower its freezing point just enough to maintain briny pockets beneath the crust. What makes these bright zones so mesmerizing is their defiance of simple categorization. They're not quite like anything else we've seen in the Kuiper Belt. Too pristine for old ice, too scattered for impacts, too static for seasons, yet too vivid to ignore. Every new observation deepens the riddle, leaving us to wonder, are we looking at geologic activity, chemical oddities, or something entirely new? Until a probe ventures out to Orcus, these gleaming enigmas will remain silent, dazzling, and utterly unwilling to give up their secrets. If there's one thing astronomers expect from the Kuiper Belt, it's bone-chilling cold, but Orcus takes it to extremes. Even by the frozen standards of the outer solar system, this dwarf planet is unnaturally frigid, with surface temperatures dipping lower than theoretical models predict. At first glance, it shouldn't be possible. Orcus orbits at roughly the same distance as Pluto, yet it's significantly colder, as if something or someone turned down the cosmic thermostat. The discrepancy isn't minor. We're talking about a variance of tens of degrees, enough to rewrite the rules of thermal behavior in the Kuiper Belt. Start with albedo. Orcus's high reflectivity should theoretically trap what little sunlight reaches it, warming the surface slightly. Think of how a white car stays cooler than a black one under the same sun, except Orcus flips that logic on its head. Despite its gleaming surface, it's colder than darker neighbors like Pluto. One explanation points to the composition of that ice. Spectra reveal an unusual abundance of ammonia mixed with water ice, a combination that might behave like a thermal mirror, bouncing radiation back into space instead of absorbing it. Ammonia's crystalline structure could act like a refrigerator lattice, efficiently shedding heat into the void. Then there's the internal heat question, or rather, the lack of it. Most dwarf planets this size generate warmth through radioactive decay in their cores, creating subtle geothermal activity. Pluto, for instance, shows signs of residual heat in its glaciers and nitrogen geysers. But Orcus's surface appears eerily inert, as if its core shut off long ago. If it lacks radioactive elements like potassium or uranium in sufficient quantities, its interior could be a frozen tomb, incapable of generating even faint warmth. Yet this raises another puzzle. How could a body this large form without the standard planetary building blocks? Did some ancient collision strip away its heat-producing materials, leaving behind a cold, dead husk? Atmospheric processes add another layer of mystery. Even tenuous atmospheres can regulate temperature, as Pluto's thin nitrogen veil does during its fleeting summers. Orcus, however, shows no evidence of a permanent atmosphere. But what if it has one that's hiding? Trace gases like methane or nitrogen might cling to its surface in ultra-thin layers, only to sublimate in brief, unpredictable bursts. These microatmospheres could act like thermal siphons, stealing warmth and venting it into space before instruments can detect them. The New Horizons mission caught Pluto's atmosphere in the act of freezing and collapsing as it moved away from the Sun. Could Orcus experience similar cycles, just on a scale too subtle for our telescopes to spot? The most unsettling possibility: Orcus isn't playing by our physics. Laboratory simulations of Kuiper Belt conditions struggle to replicate its temperature profile, suggesting missing variables. Some theorists propose exotic ices or superconductive materials in its crust, capable of channeling heat away unnaturally fast. Others wonder if its orbit exposes it to unseen cosmic winds, streams of particles or dark matter interactions that siphon off energy. Far-fetched, perhaps. But when conventional explanations fail, the universe often humbles us with truths stranger than fiction. What's clear is that Orcus's coldness isn't just a curiosity, it's a challenge. Every frigid reading forces us to reconsider how heat moves in the outer solar system, how dwarf planets evolve, and what ingredients were present in the primordial disk. Until we land a probe on its icy plains or catch it in an active state, this temperature anomaly will linger like a ghost in the data, whispering that we've barely begun to understand the rules of the cosmic deep freeze. In a realm where methane is practically a cosmic birthright, Orcus stands apart as a glaring exception. Nearly every major Kuiper Belt object, from Pluto to Makemake to Haumea, shows traces of methane ice in their spectra, a telltale fingerprint of the outer solar system's chemistry. Yet when astronomers turned their instruments toward Orcus, they found nothing. No absorption lines, no spectral signatures, just an eerie void where methane should be. This absence isn't just unusual, it's a violation of expectations, as if Orcus skipped a fundamental step in the recipe that built its icy siblings. One explanation hides in the volatile nature of methane itself. At the temperatures Orcus endures, methane ice should theoretically stick around for billions of years, clinging stubbornly to the surface. But if even a whisper of warmth seeped through, say, from a brief spike in solar activity or residual geothermal energy, that methane could have sublimated into space, leaving no trace behind. The problem: Orcus's orbit hasn't brought it significantly closer to the Sun in eons, and its surface shows no signs of past heating events. Plus, if methane escaped, why does ammonia, a far more volatile compound, still coat its surface? It's like finding a desert where all the sand vanished but the water remained. Then there's the chemical alteration theory. Methane exposed to cosmic radiation over millions of years doesn't just disappear, it transforms. Ultraviolet light and charged particles can break methane molecules apart, reforming them into complex hydrocarbons like ethane or propane. We've seen this process on Pluto's moon Charon, where methane converts into reddish tholins that darken the surface. But Orcus's spectrum shows no evidence of these byproducts either. If methane was ever present, its breakdown remnants are suspiciously absent, scrubbed clean by some unknown process. Could seasonal frost cycles have buried the evidence under fresh ice? Or did micrometeorite impacts blast away the contaminated layers, exposing pristine material beneath? The most radical possibility: Orcus never had methane to begin with. While most Kuiper Belt objects formed from the same primordial soup of ices and rock, subtle variations in their birthplaces could have led to dramatic differences. Imagine two puddles freezing on opposite sides of a valley. One collects leaves, the other stays clear. Similarly, if Orcus condensed in a pocket of the solar nebula starved of methane, it might have emerged fundamentally distinct from its neighbors. Supporting this idea is Orcus's unusually high ammonia content. Ammonia requires colder formation temperatures than methane, hinting that this dwarf planet might have originated farther out in the protoplanetary disk where certain molecules were scarce. But here's the twist: even if Orcus started methane-free, it shouldn't have stayed that way. Over billions of years, collisions with methane-rich comets should have peppered its surface with foreign ices. Pluto's landscape, for instance, bears scars from countless impacts that delivered exotic materials. Yet Orcus remains stubbornly pure, as if it repels contamination. Some researchers speculate its bright, reflective surface might act like a cosmic shield, causing impacting methane to vaporize on contact rather than sticking around. Others suggest an active resurfacing mechanism, cryovolcanism, or tectonic shifts, that constantly erases foreign deposits before they can accumulate. The implications ripple far beyond one oddball dwarf planet. If Orcus's methane deficiency stems from unique formation conditions, it could mean the Kuiper Belt's building blocks were far more diverse than we assumed. Alternatively, if some unseen process actively removes methane, we might be staring at a new class of planetary evolution, one where icy worlds self-clean through mechanisms we've yet to discover. Every time we think we've cracked the code of the outer solar system, Orcus throws a curveball, proving that even in the darkest reaches of space, nature has a flair for defiance. If Orcus's orbit is strange, its axial tilt borders on absurd. Most planets and dwarf planets in our solar system tilt modestly. Earth's 23-degree lean gives us predictable seasons, while Uranus's 98-degree roll makes it spin like a tipped wheel. But Orcus' preliminary calculations suggest its axis could be tilted past 90 degrees, possibly even exceeding 100 degrees. Picture a world spinning almost sideways, where the sun crawls along the horizon for decades before plunging into prolonged darkness. This isn't just unusual, it's a celestial anomaly that defies conventional formation models. Such an extreme tilt would unleash chaos on any semblance of seasons. On Earth, axial tilt creates orderly cycles of summer and winter. On Orcus, the sun's path would trace bizarre loops across the sky, with some regions bathed in eternal twilight while others endure centuries of frozen night. Thermal models struggle to simulate how surface ices would behave under these conditions. Methane and nitrogen frosts might migrate in unpredictable surges, gathering in craters one millennium and vanishing the next. The sheer instability could explain Orcus's patchy bright spots. Those gleaming regions might be temporary ice deposits, fleeting relics of a climate without rhythm. Theories about how Orcus got so tilted split into two camps. The first blames a cataclysmic impact. A collision with another large Kuiper Belt object could have delivered a glancing blow, literally knocking the dwarf planet onto its side. We see echoes of this in Uranus's tilt, often attributed to a primordial smash. But Orcus presents a wrinkle. Its moon Vanth orbits neatly around its equator, undisturbed by the chaos below. If a collision violent enough to tilt Orcus occurred, why didn't it disrupt or eject Vanth? Some simulations suggest the impactor struck at just the right angle and speed to reorient Orcus without destabilizing its moon, a cosmic billiard shot of improbable precision. The second camp points to gravitational resonance. Over billions of years, subtle tugs from Neptune, or even the hypothetical planet 9, could have gradually torqued Orcus's axis. This process, known as Kozai-Lidov oscillation, has been observed in exoplanet systems where distant giants warp the orbits of smaller bodies. If Orcus's orbit and tilt became locked in this dance, its axis might have slowly rolled to extremes. Supporting this idea is its orbital resonance with Neptune, which could have provided the gravitational leverage needed to tip it over. Yet critics argue this mechanism works too slowly to explain such an extreme tilt within the solar system's lifetime. Then there's the wild card, a long-lost binary companion. If Orcus once had a twin of similar mass, their gravitational interplay could have sent both objects tumbling like mismatched gears. When the companion was eventually ejected or absorbed, Orcus might have been left spinning at this bizarre angle. Binary systems are common in the Kuiper Belt. Pluto and Charon are one example, but no trace of Orcus's hypothetical twin has been found. What makes the tilt more confounding is its potential link to other mysteries. An extreme axial tilt could amplify temperature swings, driving volatile compounds like methane to sublimate unevenly, possibly explaining its absence. The tilt might also affect tidal forces on Vanth, flexing its interior in ways that could explain its dark, carbon-coated surface. Every new hypothesis circles back to the same realization. Orcus doesn't just break the rules, it rewrites them. Until a spacecraft visits this tilted oddball, we're left with simulations and speculation. But one thing's certain. If Orcus's tilt was caused by a collision, that impact didn't just change its orientation. It might have shattered our understanding of how dwarf planets evolve. And if gravitational forces alone engineered this chaos, the outer solar system is far more dynamic and far stranger than we ever dreamed. When radar signals pinged back from Orcus with bizarre inconsistencies, scientists found themselves staring at data that refused to make sense. The readings showed patches where radio waves scattered erratically, some bouncing back too sharply, others swallowed whole as if vanishing into a void. These anomalies weren't random noise, they clustered in specific regions, tracing what could only be subsurface structures hidden beneath the dwarf planet's icy shell. The implications are staggering. We might be looking at vast caverns, pockets of briny liquid, or even metallic deposits that defy everything we know about this frozen world. Take the evidence from Earth's own ice-covered extremes. Radar surveys of Antarctica have revealed subglacial lakes like Lake Vostok, where liquid water persists under kilometers of ice due to geothermal heat and pressure. On Europa, similar reflections hinted at a global ocean, a discovery later confirmed by tidal flexing. But Orcus poses a different challenge. its radar glitches don't match the clean signatures of liquid water. Instead, they suggest jagged features, perhaps ice-walled chasms carved by ancient cryovolcanic flows, or labyrinthine tunnels left behind by sublimated gases. The sharpest reflections, though, point to something even more perplexing: metallic nodules or layered minerals embedded in the ice. How could such dense materials concentrate on a world supposedly made of lightweight ices and rock? One theory invokes cryomagma. Imagine molten ice laced with ammonia or salt surging upward from Orcus's depths, carrying metallic particles scavenged from its core. As this slurry cools, it could leave behind veins of conductive material, a frozen equivalent of Earth's ore deposits. Spectral data already hints at ammonia hydrate on the surface. If it exists underground, its antifreeze properties might allow sluggish fluid dynamics even now. But here's the catch: Orcus lacks the tidal heating that powers moons like Enceladus. Without an energy source, how could these processes persist? Unless, of course, its core is richer in radioactive elements than we've assumed, simmering quietly in the dark. Then there's the cavern hypothesis. On Mars, radar anomalies revealed networks of lava tubes, hollow spaces where molten rock once drained away. Orcus's version could be cryogenic. Tunnels formed when volatile ices vaporized beneath a stabilizing crust, leaving behind empty chambers. If these voids collapsed in places, they'd create radar chaos, scattering signals where ceilings caved in, or absorbing them where gaps yawned wide. The scale could be monumental. Some models suggest chambers large enough to swallow cities, their walls glazed with exotic ice phases that only form under extreme pressure. But the wildest possibility, a buried relic from the solar system's birth. Metallic asteroids occasionally smack into Kuiper Belt objects, but they typically shatter on impact. What if Orcus captured something different, a rare nickel-iron fragment that survived intact, now lying just beneath the ice like a cosmic shipwreck? Radar reflections from metallic meteorites on Earth's poles produce similarly sharp echoes. If such an object plowed into Orcus and got encased in ice before it could fragment, it might explain the aberrant data without invoking geology at all. What makes these reflections so tantalizing is their silence. They offer no easy answers, only contradictions. Liquid pockets would suggest warmth where none should exist. Caverns imply geologic violence on a world that appears placid. And metals, they hint at a formation story we haven't even begun to unravel. Until we send a probe to orbit Orcus or punch through its ice with radar pulses of unprecedented precision, these ghostly signals will remain, a cryptic code etched into radio waves waiting to be cracked. One thing's certain: whatever lurks beneath that gleaming surface, it refuses to play by the rules. Picture two dancers separated by a crowded ballroom, moving in perfect sync without ever touching. That's the uncanny relationship between Orcus and Pluto. Despite being billions of kilometers apart, these distant worlds orbit the Sun in near-perfect harmony, locked in the same 2 to 3 resonance with Neptune. For every 3 laps Neptune completes, Pluto and Orcus each finish 2, their paths tracing elongated ellipses that never intersect yet mirror each other with eerie precision. At first glance, it seems impossible, like 2 pendulums swinging in unison across different continents. How could 2 objects so far apart, with no direct gravitational link, maintain this cosmic choreography? The answer might lie in the solar system's violent adolescence, a time when Neptune's migrations reshaped the outer darkness. Scientists call this phenomenon orbital commensurability, a delicate balance where gravitational nudges from Neptune keep both dwarf planets in rhythm. Think of it like pushing a child on a swing timed just right. Tiny forces can sustain motion indefinitely. But here's the twist: while Pluto's resonance is reinforced by its size and relative proximity to Neptune, Orcus is smaller, lighter, and more vulnerable to disruption. Its persistence in this dance suggests something extraordinary. either a shared origin story with Pluto or a hidden hand guiding both worlds. Some models propose that Neptune's outward migration billions of years ago shepherded them into these resonant orbits simultaneously, like a planetary tide lifting multiple boats. Others speculate that Orcus might have been nudged into place later, its path fine-tuned by chaotic interactions with other Kuiper Belt giants. The strangeness deepens when you examine their orbital inclinations. Pluto's orbit tilts dramatically, sweeping it high above the solar system's plane, while Orcus follows a more subdued but equally precise angle. This difference hints at divergent histories. Perhaps Pluto suffered closer encounters with Neptune, scattering it into a steeper tilt, while Orcus remained in a quieter corner of the resonance. Yet their timing stays flawlessly matched, a testament to the stability of gravitational locks over cosmic timescales. But is this synchronicity pure coincidence? The odds seem astronomical. Statistically, resonances like this should decay over time, eroded by random perturbations from passing stars or undiscovered planets. That both Orcus and Pluto have clung to their rhythms for 4 billion years suggests something more deliberate, a fossilized record of Neptune's early movements. By studying their orbits, we're essentially reading a celestial archaeology, uncovering clues about how the outer solar system settled into its current configuration. Then there's the wild card, Planet 9. Some theorists argue that an undiscovered super-Earth lurking beyond the Kuiper Belt could be subtly reinforcing these resonances, its gravity acting like an invisible conductor keeping the outer solar system's oddballs in line. If true, Orcus and Pluto might not just be dancing with Neptune, they could be part of a far larger, unseen symphony. What makes this orbital duet so mesmerizing isn't just the mechanics, it's the implication that even in the vast emptiness of space, connections persist across unimaginable distances. Orcus and Pluto may never meet, but their fates are intertwined, bound by forces older than the planets themselves. Every rotation, every loop around the sun whispers the same question. Are we seeing chaos frozen into order, or the fingerprints of a universe far more intricately linked than we ever dreamed? Naming a celestial body might seem straightforward until you dig into the fiery debates that surrounded Orcus. Unlike planets named for ancient gods by tradition, this dwarf planet's moniker ignited controversy the moment it was proposed. The International Astronomical Union reserves underworld deities for Pluto-like objects, and Orcus, borrowed from the Etruscan and Roman god of oaths and punishment, fit the bill. But critics argued it was too obscure, a deep cut from mythology that lacked the instant recognition of Pluto or Neptune. Others countered that its rarity was the point. Orcus wasn't just another icy rock, but a boundary-pushing oddity deserving of a name as distinctive as its mysteries. The clash exposed a deeper tension in astronomy, how to balance tradition with the flood of new discoveries. When Pluto was named in 1930, the solar system's map had blank spaces. Now, with thousands of Kuiper Belt objects logged, names risk feeling arbitrary or contrived. Orcus's supporters leaned into its mythological nuance. The god wasn't merely a grim reaper figure, but a punisher of broken vows, a keeper of cosmic justice. For scientists wrestling with the dwarf planet's defiance of expectations, the symbolism resonated. If Orcus broke the rules of the Kuiper Belt, maybe a name invoking divine retribution was fitting. Yet the debate didn't end there. Some astronomers pushed for 90,482, its provisional designation, arguing that numbering was more neutral. Others suggested whimsical alternatives like Proserpina's mirror, nodding to Orcus's reflective surface and its mythological ties to the underworld queen. The controversy even bled into pop culture, with online forums divided over whether the name sounded cool or like a dental instrument. What settled the argument wasn't consensus but time. As Orcus's oddities piled up the resonant orbit, the absent methane, the cryptic red spot, the name grew into its strangeness. Today, it's a reminder that labeling celestial bodies isn't just about taxonomy, it's storytelling. In a universe teeming with unnamed worlds, a contested name like Orcus does more than identify. It invites curiosity, ensuring we remember that some discoveries refuse to fit neatly into boxes, whether mythological or scientific. Orcus has always been seen as a frozen, airless world until the spectral data whispered otherwise. Hidden in the faintest absorption lines, astronomers caught fleeting glimpses of something that shouldn't be there, a whisper-thin veil of gas clinging to the dwarf planet's surface. The signals were maddeningly inconsistent, flickering in and out of detection like a radio station tuned just beyond reach. But when they appeared, they told a bizarre story. The patterns suggested nitrogen, possibly even carbon monoxide, the same volatile ices that paint Pluto's complex atmosphere. The question isn't just what these gases are doing on Orcus, but why they refuse to behave like any atmosphere we've seen before. Consider the scale of this enigma. On Pluto, nitrogen forms a hazy, dynamic shroud that ebbs and flows with the seasons, puffing up when the dwarf planet nears the sun and collapsing as it retreats. Orcus's tentative atmosphere, by contrast, appears in chaotic bursts detectable one week, vanish the next. Some observations suggest it might only manifest in localized plumes, erupting from specific regions before dissipating into space. Think of dry ice sublimating on a summer sidewalk, except here, the process happens in bizarre, unpredictable surges. The leading theory points to cryovolcanic vents cracking open under pressure, releasing pent-up gases in short-lived exhalations. But without active geology to drive such vents, where's the pressure coming from? The sporadic nature raises even stranger possibilities. Could Orcus's extreme axial tilt, that bizarre near-horizontal spin, be creating temporary cold traps? As the dwarf planet's poles slowly exchange places over millennia, frozen volatiles might migrate across the surface, pooling in shadowed basins before briefly vaporizing when exposed to sunlight. It's a phenomenon we've seen on Mars, where carbon dioxide frost sublimates in seasonal cycles, but Orcus lacks the temperature swings to explain such dramatic changes. Alternatively, micrometeorite impacts could be kicking up subsurface ices, creating transient atmospheric puffs. New Horizons observed similar impact atmospheres around Pluto's moons, but never at this scale or irregularity. Then there's the composition puzzle. Nitrogen dominates Pluto's skies because it's lightweight enough to stay aloft at frigid temperatures. Orcus, colder and smaller, shouldn't have enough gravity to hold onto nitrogen for long, yet the spectral hints persist. Carbon monoxide, if present, would be even more baffling. This molecule typically requires internal heat or sunlight to remain free-floating, neither of which Orcus has in abundance. Some researchers speculate we're seeing the last gasp of an ancient atmosphere, gases that have been locked in the ice for eons and are only now making a fleeting escape. Others wonder if solar wind or cosmic rays are blasting molecules directly off the surface, creating an ephemeral exosphere that comes and goes with the sun's activity. The most tantalizing clue might lie in what we're not seeing. When Pluto's atmosphere collapses, it leaves behind distinct frost patterns, bright deposits of nitrogen snow marking its retreat. Orcus's surface shows no such scars. If gases are escaping, they're doing so cleanly, leaving no trace. This absence suggests either a fundamentally different atmospheric chemistry or a resurfacing mechanism actively erasing the evidence. Perhaps cryovolcanic flows bury the frost before it can accumulate, or maybe the escaping gases are too sparse to leave visible residues. What makes these atmospheric ghosts so compelling is their defiance of categorization. They're not a proper atmosphere, not a static exosphere, but something in between, a phenomenon with no clear parallel in the solar system. Every flicker in the data forces us to reconsider how tenuous atmospheres form, evolve, and vanish in the outer darkness. Until a spacecraft can linger near Orcus, sniffing its vapors in real time, these spectral whispers will remain one of its most haunting mysteries, a breath of gas where none should exist, appearing and disappearing like a cosmic mirage. Most worlds in our solar system move in orderly fashion, their orbits aligned like marbles rolling along a dinner plate, but Orcus is the marble that rolled off the table. This dwarf planet circles the Sun at a steep 20-degree tilt compared to the ecliptic, that imaginary plane where planets like Earth and Mars trace nearly flat paths. Such extreme inclination isn't just unusual, it's a cosmic red flag, signaling that something dramatic once yanked Orcus out of alignment. The question isn't just how it got tilted, but why so many other Kuiper Belt objects share similar odd angles, as if the outer solar system were a gallery of knocked-over bowling pins. The leading theory takes us back 4.5 billion years to a time when Neptune went rogue. Planetary migration, the idea that giant planets shuffled outward in the solar system's infancy, could explain the chaos. As Neptune lumbered away from the Sun, its gravity would have stirred up the primordial Kuiper Belt, scattering objects like Orcus into bizarre orbits. Picture a bulldozer plowing through gravel. Some rocks get flung high, others deflect at odd angles. Computer simulations show this process can reproduce many of the Kuiper Belt's inclined orbits, but Orcus pushes the limits. Its tilt is too pronounced for a simple nudge. It likely endured a series of gravitational kicks, perhaps from Neptune and other now ejected ice giants. Yet there's a wrinkle. Objects tossed by Neptune's migration typically end up with eccentric, elongated orbits. Orcus, while tilted, maintains a relatively circular path. This contradiction hints at a gentler origin for its inclination, maybe a distant encounter with another massive body, something too far away to distort its orbit but close enough to tip it over. Enter Planet 9. This hypothetical super-Earth, if it exists, could have torqued Orcus's axis through gradual nudges over eons, a process called quasi-Lidov oscillation. The same mechanism tilts some exoplanets to extreme angles, their orbits warped by unseen companions. The plot thickens when you compare Orcus to its cosmic cousins. Pluto, despite sharing a resonant orbit with Neptune, orbits closer to the ecliptic. Sedna, another inclined Kuiper Belt object, ventures so far out it may have been tugged by passing stars. Orcus sits in a Goldilocks zone, too tilted for a quiet history, yet too stable for a violent one. This paradox suggests multiple influences. Perhaps an early encounter with Neptune set the tilt, while resonant forces later stabilized its path. What makes this inclination more than orbital trivia is its connection to Orcus's other anomalies. A steep axial tilt could amplify seasonal extremes, explaining those transient atmospheric whispers. It might also affect how sunlight scours the surface, leaving some regions bright while others gather dark organics. Every new calculation reinforces the same realization: Orcus didn't just tip by accident. Its crooked path is a fossil record of the outer solar system's turbulent youth, a cryptic clue waiting to be deciphered. Vanth's orbit around Orcus shouldn't exist, at least not according to conventional wisdom. Most moons in the Kuiper Belt follow eccentric, irregular paths, the scars of violent captures or chaotic collisions. Yet Vanth glides along a near-perfect circle, hugging Orcus so closely it defies expectations. This isn't just unusual, it's a cosmic contradiction, a moon that behaves like it was sculpted by gentle hands rather than celestial chaos. The mystery deepens when you realize how rare this configuration is. Pluto's moon Charon, the Kuiper Belt's other famous companion, orbits tightly because it was born from a cataclysmic impact that left it tidally locked. Vanth, however, shows no signs of such trauma. Its orbit is too circular, too pristine, as if it settled into place without the usual violence. Theories about how this happened split into two camps. The first invokes tidal forces, the same gravitational tug of war that smooths orbits over billions of years. Earth's moon, for example, started with a wilder path before tides rounded it into the near circle we see today. But Vanth's proximity to Orcus makes this explanation shaky. Tidal forces weaken dramatically with distance, and Vanth orbits far enough that it shouldn't have fully circularized in the solar system's lifetime. Unless, of course, Orcus once spun much faster, accelerating the process. Some models suggest a massive impact could have sent Orcus into a rapid initial spin, its rotation slowing over eons as tidal friction transferred energy to Vanth. Yet Orcus's current rotation rate doesn't betray this turbulent past, leaving the theory on shaky ground. The second camp proposes a gentler origin, a cosmic dance instead of a demolition derby. Imagine Vanth drifting near Orcus in the early solar system, their mutual gravity gradually pulling them together like partners finding rhythm. This dynamic capture scenario would require just the right conditions, a slow approach, minimal interference from other objects, and perhaps a wisp of gas left over from the protoplanetary disk to nudge Vanth into orbit. While rare, such delicate captures aren't impossible. Neptune's moon Triton, thought to be a captured Kuiper Belt object, may have undergone a similar courtship. But Vanth's orbit is even more refined, raising eyebrows. If it was captured, why didn't subsequent impacts or gravitational jostles distort its path? Then there's the composition clue. Vanth's dark, carbon-rich surface suggests it might have originated farther out in the Kuiper Belt, where ultra-red objects like Arakoth reside. If true, its journey to Orcus would have been long and perilous, making its precise orbit even harder to explain. Some researchers speculate that Vanth arrived with a cloud of debris, its orbit circularized by friction with this now vanished material. Others wonder if Orcus once had a diffuse ring system, whose gentle drag sculpted Vanth's path like a potter shaping clay. What makes Vanth's orbit so compelling isn't just the mechanics, it's the implications. If tidal forces alone shaped it, we've underestimated how quickly small bodies can evolve. If capture formed it, the early Kuiper Belt was far calmer than we thought. And if some hybrid process is at work, we might be staring at a completely new class of moon formation. Every observation peels back another layer, revealing a story written not in collisions and chaos, but in patience and precision. Vanth doesn't just orbit Orcus, it silently challenges our assumptions about how the solar system's smallest worlds find their partners. Some of the most bizarre objects in the Kuiper Belt come in pairs, worlds that once danced separately before embracing in slow-motion collisions, merging into misshapen cosmic snowmen. New Horizons showed us the stunning example of Arakoth, that bi-lobed relic frozen in time since the solar system's birth. Now, tantalizing evidence suggests Orcus might share this strange anatomy, not a single sphere, but two primordial bodies pressed together like a frozen dumpling spinning in the void. Shape models based on light curve data reveal odd asymmetries in Orcus's silhouette. As it rotates, brightness fluctuations hint at dramatic topographical variations, perhaps a bulging midsection or abrupt changes in curvature that single bodies rarely exhibit. The most compelling data comes from stellar occultations when Orcus passed in front of distant stars. The way it blocked starlight didn't match a smooth sphere. Instead, the shadow's edges suggested abrupt transitions, as if something was kinked or pinched at the waist. Some astronomers interpret this as the telltale seam of a contact binary, where two smaller planetesimals gently merged rather than violently colliding. If true, the implications rewrite Orcus's origin story. Most large Kuiper Belt objects like Pluto grew through violent impacts, shattering and reassembling in chaotic pileups. A gentle merger implies Orcus formed in a quieter corner of the primordial disk, where icy pebbles orbited slowly enough to kiss rather than crash. This would make it a time capsule of sorts, a preserved snapshot of how building blocks came together before gravity stirred the pot. Supporting this idea is Orcus's uncanny density. Preliminary estimates suggest it's less dense than expected for a solid ice-rock mix, as if hollow spaces lurk beneath its crust, exactly what you'd find if two loosely packed bodies left gaps when they joined. Yet puzzles remain. Contact binaries tend to have elongated, peanut-like shapes, while Orcus's overall form appears more spherical. Some researchers argue this could mean its lobes were nearly equal in size, their union so ancient that eons of geologic adjustment smoothed the seams. Others propose an intermediate scenario. Perhaps Orcus suffered a glancing impact that deformed it without fully breaking it apart, leaving one side swollen like a half-inflated balloon. The wild card is Vanth. If Orcus is a merger, its moon might be debris from that encounter, though Vanth's dark composition complicates the narrative. What makes this theory so electrifying isn't just the shape. It's the chance to test fundamental ideas about planetary growth. If Orcus is a contact binary, it means gentle mergers played a bigger role in building the outer solar system than we thought. And if not, those odd light curves hint at something even stranger, a world sculpted by forces we've yet to name. Every new observation leaves us wondering, are we seeing two become one or something more mysterious still? Orcus doesn't just spin, it flickers like a distant candle in the cosmic dark, its brightness pulsing in ways that defy simple explanation. Most rotating objects in the solar system follow predictable light curves, their reflective surfaces creating smooth, rhythmic brightness variations as they turn. But when astronomers trained their telescopes on Orcus, the patterns that emerged were anything but regular. Instead of the steady rise and fall expected from a spinning sphere, the data showed erratic spikes and dips, fluctuations too sharp to blame on rotation alone. The anomalies weren't just noise, they hinted at something far stranger lurking on or around this dwarf planet, a puzzle written in flickering starlight. One leading suspect, surface irregularities so extreme they warp the light curve entirely. Picture towering ice cliffs or deep, shadow-choked basins, features stark enough to cast dramatic silhouettes against the sun's feeble glow. On Pluto, for instance, the heart-shaped Tombaugh Regio creates measurable brightness swings as it rotates into view. But Orcus's variations are more jagged, as if its terrain is a chaotic patchwork of reflective plateaus and light-swallowing chasms. Some researchers speculate these could be cryovolcanic constructs, frozen geysers that built up jagged spires over eons. Others propose impact scars so fresh their steep walls haven't yet eroded into gentler slopes. Either way, the math is clear. These aren't ordinary craters or plains. They're fractures in the rulebook, landscapes that shouldn't exist on a world this small and cold. Then there's Vanth's role in this celestial light show. Orcus's moon orbits close enough that its shadow could theoretically skim across the dwarf planet's surface, briefly dimming the combined brightness seen from Earth. But here's the catch. Vanth's orbit is too regular, too circular to explain the erratic dips in the data. Shadows from moons like Pluto's Charon create predictable, repeating patterns, not the wild inconsistencies observed here. Unless, of course, Vanth isn't the only thing casting shadows. If Orcus harbors undiscovered debris, a faint ring system or a cloud of dust, its intermittent passage could scatter light unpredictably. The problem, no such features have been spotted, leaving astronomers to wonder if they're chasing ghosts. The most tantalizing possibility involves albedo anomalies, regions where the surface reflectivity changes abruptly. On Saturn's moon Iapetus, a mysterious dark hemisphere contrasts with a bright one, creating stark light curve asymmetries. Orcus might host similar extremes, but with a twist. Its bright patches could be dynamic, shifting over time as volatile ices sublimate and recondense. Imagine sunlit zones where ammonia-rich frost briefly blooms before vanishing, creating fleeting highlights in the curve. Seasonal changes can't explain the speed of these fluctuations, though. Unless, that is, Orcus's extreme axial tilt triggers microseasons, brief, localized cycles of frost and thaw unlike anything else in the Kuiper Belt. What makes these light curves so mesmerizing is their refusal to fit any single narrative. They're not just noise, not just shadows, not just terrain, but maybe all three, woven into a pattern we're only beginning to decode. Every new observation deepens the intrigue, leaving us with more questions than answers. Is Orcus's surface alive with changes too subtle for our telescopes to resolve? Are unseen forces sculpting its light in real time? Or are we glimpsing something far more profound? A celestial cipher that, once cracked, could rewrite how we understand the outer solar system's silent, flickering worlds. One of the most baffling sights on Orcus isn't what's there, it's what's missing. Across vast stretches of this distant world, telescopes reveal plains so smooth they seem polished, landscapes unnervingly devoid of the pockmarked history we expect from Kuiper Belt objects. In a region where cosmic collisions are as common as raindrops on Earth, these unblemished zones stand out like blank pages in a scarred notebook. The contradiction stings. If Orcus has existed for billions of years, why doesn't its surface bear the same cratered roadmap as Pluto, its cosmic twin? The answer might rewrite our understanding of how icy worlds evolve, or hide something far stranger beneath their frozen skins. First, consider the numbers. Crater counts are the solar system's history books, recording every major impact since the late heavy bombardment. On Pluto's ancient terrain, some regions show over 500 visible craters per million square kilometers. Orcus's smoothest zones barely a dozen. That discrepancy suggests either impossibly good luck, like dodging every raindrop in a monsoon, or an active process erasing evidence of impacts faster than they accumulate. Cryovolcanic resurfacing is the prime suspect. Imagine slushy plumes of water, ammonia, and methane erupting from subterranean chambers, flooding the surface like celestial lava before freezing into glassy plains. We've seen this on Neptune's moon Triton, where geysers spew nitrogen frost that carpets older features. But Orcus lacks the tidal heating that powers Triton's activity, leaving scientists scrambling to explain what could possibly fuel such eruptions in this frozen hinterland. The erosion theory offers a different twist. On Earth, wind and water sculpt landscapes over millennia. In the airless void of the Kuiper Belt, other forces might play the role of cosmic sandpaper. One hypothesis points to seasonal volatiles cycling delicate ices like nitrogen or carbon monoxide sublimating under fleeting sunlight, then recondensing elsewhere, gradually filling craters like self-healing asphalt. Pluto's Sputnik Planitia demonstrates this process, its heart-shaped basin refreshed by glacial flows. But Orcus's extreme cold and tenuous atmosphere make sustained volatile movement unlikely. Unless, that is, its axial tilt creates microclimates where frost migrates in slow, unpredictable waves, erasing topography over eons. Then there's the wild card, electrostatic levitation. Laboratory experiments show that under ultra-low pressures, sunlight can electrically charge ice grains, making them hover just above the surface. Over time, this fairy dust effect could redistribute material, filling depressions until the terrain flattens like a cosmic Zen garden. Mars's polar caps exhibit similar processes, but Orcus would take it to extremes, with electrostatic forces acting as invisible landscapers. The catch: no other known world relies on this mechanism for large-scale erosion, leaving theorists to wonder if they're grasping at straws. Perhaps the most unsettling possibility is that Orcus's craters aren't missing at all, they're hiding. Radar anomalies hint at subsurface voids where ancient impact basins might have collapsed inward, swallowed by caverns of methane clathrate or nitrogen ice. On Pluto, vast pits called penitents form when sunlight carves intricate patterns into volatile rich ice. Could Orcus host similar features on a monumental scale, its craters dissolving into labyrinthine sinkholes? Without close-up imagery, these ghost craters remain speculative, their absence a silent provocation. What makes this paradox so compelling is its defiance of every expectation. Smooth terrain shouldn't exist this far out, not without a visible energy source or detectable atmosphere. Yet there they gleam, pristine as fresh snow under a winter moon. Whether through cryovolcanic whispers, electrostatic trickery, or some unseen geologic alchemy, Orcus is clearly playing by rules we've yet to decipher. Each smooth plane is a cipher, a riddle carved not in stone but in the eerie absence of scars. The infrared spectrum of Orcus should be a clean, predictable readout, a simple fingerprint of ices and rock under the feeble glow of distant sunlight. Instead, astronomers keep stumbling over spectral bumps, tiny but stubborn anomalies in the data that refuse to fit any known material. These absorption lines lurk at wavelengths between 3.5 and 4 microns, a range where molecules like methane or methanol usually leave their mark. But Orcus's bumps don't match any familiar compounds cleanly. They're too sharp, too offset, as if something in the ice is whispering in a language we haven't yet decoded. At first, scientists dismissed these quirks as telescope artifacts, ghosts in the machine caused by Earth's atmosphere or instrumental noise. But when multiple observatories, from the Spitzer Space Telescope to ground-based spectrographs in Chile, recorded the same oddities, the reality set in. These features are real, and they're coming from Orcus itself. The hunt for their origin splits into 3 camps, each more tantalizing than the last. The organic faction points to complex hydrocarbons tholins or polycyclic aromatic hydrocarbons PAR as the culprit. These carbon-rich molecules form when simple ices like methane get bombarded by radiation, knitting themselves into reddish-brown goo. We've spotted them on Titan, Pluto, and even comets. But Orcus's bumps are offset from known tholin signatures, suggesting either a novel variant or a mixture with something else entirely. Some researchers propose the presence of cyanide compounds, which absorb in this range and could hint at probiotic chemistry frozen in time. The problem: Orcus lacks the atmospheric haze or surface coloration typically linked to organic sludge. If these molecules exist, they're hiding in plain sight, their spectral hints defying visual confirmation. Then there's the salt argument. Laboratory simulations show that ammonia hydrates mixed with salts like sodium chloride or potassium carbonate can produce similar infrared quirks. On Europa, salts from a subsurface ocean stain surface fractures, betraying hidden liquid below. If Orcus harbors briny pockets, these dissolved minerals might have seeped upward through cracks, freezing into crystalline patterns that catch sunlight just wrong. The challenge: salts usually require liquid water to mobilize, and Orcus's interior is presumed far too cold for even ammonia-laced brines to flow. Unless, of course, radioactive decay or residual heat from its formation still lingers, keeping a sliver of ocean alive in the dark. The wild card: instrumental artifacts, but not in the way you'd expect. Some theorists suggest these bumps aren't caused by surface materials at all, but by an optical illusion known as the Christiansen effect. When light interacts with particles of a specific size, it can scatter in ways that mimic absorption features. On Mars, fine dust creates spectral false positives that baffled researchers for years. If Orcus's surface is dusted with micron-sized ice grains, perhaps shaped by eons of sublimation and recondensation, they could be bending light into these mysterious patterns. Yet no other Kuiper Belt object displays such pronounced Christiansen features, leaving this theory dangling on the edge of plausibility. What makes these spectral bumps so electrifying is their refusal to conform. They're not quite organics, not quite salts, not quite noise, but something lingering in the gaps between. Every new observation sharpens the paradox, forcing us to wonder: are we seeing chemistry we don't understand, geology we can't explain, or physics playing tricks in the frozen dark? Until a probe flies close enough to taste Orcus's surface directly, these infrared riddles will remain a cosmic koan written in wavelengths, waiting for its answer. Measuring Orcus turns out to be far trickier than anyone expected because, depending on who you ask, this dwarf planet is either the size of Texas or barely larger than Arizona. Estimates of its diameter swing wildly from 700 to 950 kilometers, a margin of error you'd never tolerate for something as fundamental as a world's basic dimensions. The root of this cosmic measuring tape crisis, a perfect storm of scientific headaches where brightness, shape, and distance conspire to keep Orcus's true scale just out of reach. Start with albedo, the reflectivity that makes Orcus shine like a frozen disco ball in the void. Most Kuiper Belt objects are dim, sooty things, their surfaces darkened by eons of radiation baking carbon-rich gunk onto their ice. But Orcus's exceptional brightness throws off the math. When astronomers use thermal emissions to estimate size, they assume a certain balance between absorbed sunlight and radiated heat. A brighter object could either be large and moderately reflective or smaller and extraordinarily shiny. Orcus's glaring surface, possibly due to fresh ammonia-laced ice, skews these calculations dramatically. Early observations pegged it at roughly 950 kilometers, but later studies accounting for its high albedo slashed that estimate by nearly a third. Then there's the shape problem. Light curve analysis suggests Orcus isn't a perfect sphere but an oblong mass tumbling through space. If confirmed as a contact binary, two smaller bodies fused together, its dimensions get even murkier. A stretched shape means its apparent size changes depending on which angle faces Earth during observations. Imagine trying to measure a football by only glimpsing it end-on versus side-on. Without a consistent silhouette, precision crumbles. The wild card, Vanth. Orcus's moon orbits so close that separating their combined light for measurements is like trying to read a street sign through fog. Until New Horizons-style flybys become feasible, we're left stitching together fragments of data. Radar echoes here, occultation timings there, each method whispering a different number. This isn't just academic nitpicking. Pin down Orcus's true size and suddenly its density, and thus its internal structure, snaps into focus. A larger, puffier Orcus implies vast subsurface caverns. A smaller, denser one suggests a rock-rich core shrouded in improbably bright ice. For now, this cosmic Rorschach test remains unresolved. Its contradictions a reminder that even in an age of precision astronomy, some truths refuse to be neatly measured. Most worlds in the Kuiper Belt whirl like frenetic tops, spinning fast enough to complete a full rotation in just hours. But Orcus lingers. This dwarf planet takes a sluggish 17 hours to turn once, a pace so leisurely it defies expectations for an object of its size. The puzzle isn't just why it's slow, it's how something so small could lose so much momentum. Earth's moon breaks our planet's spin over billions of years through tidal forces, but Orcus and Vanth are tiny by comparison, their gravitational tug far too weak to explain such dramatic braking. Unless, of course, we're missing a crucial piece of this cosmic slowdown. Tidal locking is the usual suspect. Just as our moon's gravity gradually synchronized Earth's rotation, Vanth could be exerting a similar brake on Orcus. The math, though, doesn't quite add up. For tides to slow Orcus this much, Vanth would need to be far more massive or far closer than it is. Current models suggest it would take tens of billions of years longer than the age of the solar system for Vanth alone to drag Orcus to this crawl, yet here we are. One radical explanation: Vanth wasn't always so distant. If it formed closer in and migrated outward over eons like Triton's decaying orbit around Neptune, it could have torqued Orcus's spin much faster in the past. But orbital mechanics make this scenario unlikely without some external force nudging the moon outward. Then there's the primordial spin theory, the idea that Orcus never rotated quickly to begin with. Most Kuiper Belt objects inherited rapid spins from the chaotic collisions that built them, like figure skaters pulling in their arms to accelerate. Orcus might be an exception, coalescing from a gentler merger that imparted little angular momentum. Imagine two ice chunks barely touching as they came together, their combined rotation barely more than a lazy drift. This would fit with the contact binary hypothesis, where Orcus's two lobes fused without the usual violence. Supporting this are simulations showing that slow-spinning binaries can form in the outer solar system's low-energy environments, where impacts are rare and gentle. Yet even this tidy explanation frays at the edges. If Orcus formed slow, why don't more Kuiper Belt objects share its languid pace? And how does it reconcile with Vanth's seemingly youthful orbit, which should have been disrupted by any primordial slowdown? The answer might lurk in a forgotten chapter of Orcus's history, a time when it wasn't alone. Some theorists propose a long-lost third body, perhaps a second moon that once danced with Vanth in a complex gravitational waltz. As the trio interacted, the interloper could have siphoned off Orcus's rotational energy before being ejected into the void. We see echoes of this in Neptune's moon system, where Triton's capture likely hurled other moons into chaotic orbits. The most haunting possibility, Orcus's slow spin isn't just a relic, it's an ongoing process. Subtle forces, from solar radiation pressure to the faint push of escaping gases, might still be tapping the brakes, a deceleration so gradual we'd never notice it in human timescales. Every rotation, every loop around the sun could be stretching the interval imperceptibly longer, a cosmic slowdown written in increments too small to measure. Until we land a probe on its surface or track its spin over centuries, this enigma will endure. A world turning not just against the void, but against our understanding of how time and gravity sculpt the dance of the cosmos. Among the many riddles Orcus presents, none are as fleeting or as fiercely debated as the so-called ghost tale. In a handful of telescope images, most notably from the Hubble and Subaru observatories, astronomers spotted something peculiar, a wispy, asymmetrical smudge extending from Orcus's trailing hemisphere, resembling the faint brushstroke of a comet's trail. The anomaly appeared in less than 5% of observations, flickering in and out of visibility like a cosmic will-o'-the-wisp. It wasn't consistent enough to be a surface feature, nor transient enough to dismiss as random noise. This spectral appendage shouldn't exist on an object as cold and supposedly inert as Orcus, and yet there it was, a whisper of something escaping into the void. The immediate suspicion, outgassing the sublimation of volatile ices into space, a process that fuels comet tails across the solar system. Pluto's tenuous atmosphere proves even distant worlds can exhale trace gases when warmed by the sun. But Orcus's orbit keeps it perpetually frozen. Temperatures rarely climb above -230 degrees Celsius, far too cold for nitrogen or methane to vaporize en masse. Unless, of course, something's stirring beneath the ice. One radical theory posits cryovolcanic vents cracking open under pressure, releasing pockets of ancient gases trapped since Orcus's formation. These sporadic bursts could explain the tale's inconsistency, a geyser-like belch of volatiles freezing instantly into glittering dust as they hit the vacuum. Europa's plumes demonstrate similar behavior, though driven by Jupiter's tidal forces. Without such external energy, what could crack Orcus's icy shell? Then there's the dust hypothesis. Micrometeorites bombarding Orcus's surface might be kicking up clouds of ice particles, creating a temporary halo. Saturn's E-ring, fed by Enceladus's eruptions, shows how fine debris can linger in orbit. But Orcus lacks the gravity to maintain such a cloud for long, unless the particles are electrically charged, riding solar wind like a celestial sandstorm. Laboratory experiments confirm ultraviolet light can levitate ice grains on airless worlds, a phenomenon observed on the Moon. If Orcus's extreme tilt exposes fresh ice to sunlight, electrostatic forces might launch microscopic crystals into space, forming a cobweb-thin trail that dissipates within hours. The darkest horse in this race, pure instrument error. Hubble's advanced camera for surveys has documented similar ghost features around other Kuiper Belt objects, often traced to scattered light or cosmic rays hitting the detector. The Subaru observations, though, complicate this dismissal. Taken years apart with different instruments, the persistence of the tail across datasets makes glitches statistically unlikely. Unless, of course, both telescopes fell victim to the same rare optical illusion, perhaps light diffracting around Vanth's orbit, or an undiscovered background object photobombing the frame. What makes this phantom tail so tantalizing is its refusal to be categorized. Too sporadic for geology, too structured for noise, it exists in the liminal space between artifact and revelation. If real, it hints at processes we've never witnessed in the Kuiper Belt, a dormant world stirring fitfully in its icy sleep. If false, it's a testament to how even our best instruments can tease us with cosmic mirages. Until a spacecraft ventures close enough to sniff Orcus's trailing edge, this wispy enigma will remain suspended between discovery and myth, a shadow on the lens of science. One of the most persistent headaches in studying Orcus comes not from what telescopes detect, but from how wildly their readings disagree. Depending on which observatory you consult, this dwarf planet's albedo, the percentage of sunlight it reflects swings between 30 and 50%, a discrepancy that would be laughable if it weren't so confounding. For context, that's the difference between fresh snow and wet asphalt in cosmic terms. How can one object's brightness be so hotly contested? The answer lies in a perfect storm of observational nightmares where distance, surface quirks, and the limitations of our instruments conspire to keep Orcus's true nature just out of focus. Start with the challenge of measuring something so faint and far-flung. Earth-based telescopes must peer through our atmosphere's turbulent soup, which distorts infrared and visible light differently. Adaptive optics help, but subtle variations in atmospheric water vapor or dust can skew albedo estimates by whole percentage points. Then there's the phase angle problem, the angle at which sunlight hits Orcus and bounces back to us. Unlike the Moon, which we view at relatively consistent angles, Orcus's elongated orbit means we see it illuminated from dramatically different perspectives over decades. A slightly roughened patch of ice might appear dazzling when sunlight strikes it head-on, then vanish into shadow when observed obliquely, but the real culprit might be Orcus itself. Most Kuiper Belt objects wear their reflectivity uniformly like a coat of dull paint. Orcus, however, seems stitched together from mismatched fabrics. High-resolution spectra reveal stark regional divides, sprawling plains of near-mirror-like water ice abut dark, organic-rich terrain, creating a surface where reflectivity could swing by 30% within a single hemisphere. Throw in those puzzling bright patches, possibly fresh cryovolcanic deposits, and you have a world that changes its appearance depending on which slice happens to face Earth during observations. It's like trying to measure the shininess of a disco ball while only glimpsing one mirrored tile at a time. The plot thickens when you factor in wavelength dependence. Orcus's albedo isn't just inconsistent between studies, it fluctuates across the electromagnetic spectrum. Observations in visible light often peg it as brighter than near-infrared readings, a mismatch that hints at something stranger than mere observational error. Ammonia hydrate, one of the key ices detected on Orcus, exhibits strong spectral features at specific wavelengths, meaning its reflectivity isn't constant across all colors of light. If some telescopes prioritize certain wavelength bands over others, as they often must to cut through noise, they'll capture fundamentally different portraits of the same world. Compounding the confusion is Vanth's glare. Orcus's moon orbits close enough that its darker surface can contaminate albedo measurements, especially when telescopes lack the resolution to separate the pair. Early studies that treated the system as a single point of light inevitably averaged Vanth's charcoal tones with Orcus's brilliance, producing misleading middle ground values. Even today, disentangling their contributions requires sophisticated modeling and assumptions about Vanth's own poorly understood reflectivity. What makes this albedo puzzle more than academic is what it implies about Orcus's hidden engines. That dazzling brightness suggests active resurfacing, a process erasing darker impact craters and organics faster than they can accumulate. Yet no energy source obvious enough to power such renewal has been detected. Every conflicting measurement forces us to wonder, are we seeing a world locked in frozen stasis, or one where unseen forces, cryovolcanism, electrostatic levitation, or something entirely novel are quietly rewriting its surface? Until a spacecraft finally trains its cameras on Orcus's mercurial face, these discrepancies will endure, a reminder that even in an age of precision astronomy, some truths refuse to be pinned down by a single number. Beyond the bustling realm of Neptune and the scattered Kuiper Belt, something eerie happens. Objects suddenly vanish. Astronomers call it the Kuiper Cliff, a dramatic drop-off in the number of detectable bodies beyond 50 astronomical units, as if someone drew a cosmic fence at the edge of the solar system. The strangest part, Orcus, with its peculiar orbit, sits tantalizingly close to this invisible boundary, prompting a spine-tingling question. Is this dwarf planet not just a resident of the Kuiper Belt, but a sentinel guarding its outer edge? The statistics alone raise eyebrows. Past 50, the population of Kuiper Belt objects plummets by nearly 90%, a decline far steeper than standard models predict. Some theories blame Planet Nine's hypothetical gravity shepherding objects inward, while others suggest the primordial disk of planet-building materials simply ran out of steam at this distance. But Orcus complicates the story. Its orbit perched just inside this mysterious threshold at 48 mirrors the cliff's location with uncanny precision. Could its resonance with Neptune be more than coincidence? Simulations show that objects nudged into orbits like Orcus's act as dynamical anchors, their gravity subtly repelling other bodies over billions of years. Picture a boulder in a stream diverting the current around it, except here, the current is made of frozen planetesimals, and the boulder is a dwarf planet sculpting the edge of the known solar system. Yet contradictions linger. If Orcus marks a boundary, why don't other resonant objects share its placement? Pluto, locked in the same 2 to 3 resonance, roams as far as 50 without triggering a cliff. The difference might lie in inclination. Orcus's steep orbital tilt, that bizarre 20-degree lean, could amplify its gravitational reach, creating a 3-dimensional barrier that most Kuiper Belt objects can't cross. Think of it as a celestial speed bump angled just right to deflect traffic. Supporting this idea are the handful of extreme trans-Neptunian objects like Sedna, whose freakishly elongated orbits hint at past encounters with a massive perturber. Could Orcus's ancient interactions have helped slingshot them into the abyss, thinning the population beyond the cliff? The plot twists when you consider the missing methane. Most Kuiper Belt objects beyond 50 are rich in volatile ices, suggesting they formed farther out where temperatures kept these compounds stable. Orcus's methane deficiency implies it might have originated closer in, only to migrate outward later, possibly carrying the seeds of the cliff with it. If it drifted into its current position during Neptune's planetary migration, its gravity could have swept the region clean, like a bulldozer pushing debris to a construction site's edge. But the wildest theory, Orcus isn't the boundary's architect, it's its prisoner. Some models propose the cliff isn't a true edge but an observational blind spot. Beyond 50, objects move so slowly they're harder to detect, and their surfaces may darken over time from radiation, rendering them nearly invisible to telescopes. Orcus, with its freakishly high albedo, might simply be one of the few bright enough to still catch our eye in this dim frontier. If true, the Kuiper Cliff isn't a wall, it's a veil, and Orcus is the lone dancer we can still glimpse through the cosmic fog. Whether gatekeeper, relic, or illusion, Orcus's orbit forces us to confront how little we understand about the solar system's outer limits. Every new discovery peels back another layer, revealing a frontier that refuses to fit our maps, a place where rules bend, numbers lie, and a single icy world might hold the key to the last great boundary we've yet to cross. Imagine a spacecraft finally piercing the darkness around Orcus, its cameras revealing every crack and canyon on that gleaming, alien surface. After decades of squinting through telescopes at this distant enigma, a dedicated flyby wouldn't just answer questions, it would rewrite the textbook on Kuiper Belt worlds. Think of the revelations New Horizons brought at Pluto: nitrogen glaciers, towering ice mountains, and a sky-scraping haze that defied all predictions. Yet for all its triumphs, that mission left a glaring gap in our understanding because Pluto, it turns out, isn't the template for the outer solar system. It's the outlier. Orcus, with its freakish brightness, missing methane, and phantom atmosphere, represents the mysteries we never saw coming, and a flyby here could crack open secrets even Pluto couldn't reveal. First, consider the surface. Spectra from Earth hint at ammonia hydrate, a compound rarely seen in such abundance, yet we've no idea how it's distributed. Is it pooled in frozen seas, laced through cryovolcanic flows? A flyby's infrared scanners could map its exact locations, revealing whether it's a relic from Orcus's formation or the product of ongoing geology. Then there's that infamous red spot. Up close, high-resolution images could distinguish between impact debris, cryovolcanic deposits, or something far stranger, like irradiated organic sludge seeping from beneath the ice. Every crater, every ridge would be a time capsule, preserving clues about the Kuiper Belt's violent past. But the real prize might lie in Vanth. Pluto's moon Charon taught us that binary worlds harbor planetary-scale drama, canyons, fractures, and even potential cryovolcanoes. Vanth's dark, carbon-stained face suggests a history even more chaotic. A flyby could settle the debate over its origin once and for all. Spectrometers would analyze its surface for xenoliths, fragments of Orcus's crust blasted into orbit by an ancient collision. Or perhaps they'd find isotopes matching ultra-red Kuiper Belt objects, proving Vanth was captured from the solar system's darkest reaches. And let's not forget the ghostly possibility of a second moon. A spacecraft's cameras could scan the darkness where Hubble saw only flickers, either confirming Vanth's existence or burying the mystery for good. Then there's the underground. Radar pulses from a passing probe could penetrate miles of ice, hunting for those tantalizing subsurface anomalies. Are they brine pockets, metallic intrusions? Vast caverns hollowed out by escaping gases. On Europa, similar techniques revealed a global ocean. At Orcus, they might expose a frozen labyrinth, its walls glazed with exotic ices that only form under extreme pressure. Even the dwarf planet's temperature discrepancies could finally make sense, with thermal mappers pinpointing hotspots that betray residual geothermal activity or the chilling absence of it. The contrast with Pluto would be revelatory. Where Pluto dances with seasons and atmospheres, Orcus seems locked in a cryogenic deep freeze, yet both share eerily similar orbits. A flyby could test whether they're cosmic siblings shaped by the same forces, or strangers that stumbled into the same gravitational rhythm. Imagine discovering that Orcus's resonance with Neptune is subtly different, hinting at unseen perturbations from Planet 9. Or that its missing methane was literally blasted away by eons of solar wind, leaving behind a planetary fossil. Advocating for this mission isn't just about solving Orcus's puzzles, it's about redefining what's possible in the outer darkness. New Horizons showed us one flavor of dwarf planet. A visit here would reveal another, proving the Kuiper Belt is as diverse as the inner solar system. The cost comparable to a mid-budget Hollywood film. The payoff, a legacy of discovery that could span generations. Every light curve anomaly, every spectral bump, every flicker of that ghost tail is a question only a spacecraft can answer. Until then, Orcus remains a mirror not just reflecting sunlight, but our own longing to explore the edges of the unknown. Orcus doesn't just defy expectations, it shatters them, leaving behind a trail of cosmic riddles that rewrite the rulebook for the outer solar system. From its baffling lack of methane to those eerie radar anomalies hinting at hidden voids beneath its icy crust, every discovery peels back another layer of mystery. Why does a world so distant gleam brighter than fresh snow, while its moon Vanth lurks in darkness like a charcoal spectre? How can something so small maintain an orbit so perfectly synchronized with Pluto's, as if Neptune itself choreographed their dance? And what force keeps its surface unnervingly smooth, erasing eons of impacts like a celestial etch-a-sketch? The contradictions pile up faster than answers. That ghostly red stain, too vivid for radiation, too isolated for cryovolcanism, whispers of chemistry we've never encountered. The flickering ghost tail that comes and goes like a cosmic will-o'-the wisp defies even the boldest theories. And let's not forget the temperature paradox, a world that reflects sunlight like a mirror yet chills to depths colder than models predict, as if its very laws of thermodynamics are tilted along with its axis. Even Vanth's uncannily circular orbit mocks our understanding of moon formation, a silent rebuke to centuries of celestial mechanics. What makes Orcus truly extraordinary isn't just the individual puzzles, it's how they intertwine, painting a portrait of a world that refuses categorization. Is it a dormant cryovolcanic giant, a captured interstellar rogue, or a relic from a solar system we no longer recognize? Each hypothesis collapses under the weight of new contradictions, leaving scientists torn between awe and frustration. This isn't just about filling gaps in our knowledge, it's about realizing how vast those gaps truly are. So here's the challenge: which Orcus mystery keeps you up at night? Is it the phantom atmosphere that flickers in and out of existence, the way its orbit guards the Kuiper cliff like a cosmic sentinel? Or the chilling possibility that beneath all that ice lies something no model could predict? Drop your thoughts in the comments. We're all detectives in this grand celestial mystery. And if you crave more enigmas from the frozen fringes of space, hit subscribe. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and Orcus is proof. The answers, they're still out there, waiting in the dark.